Before we move on to the last two examples, I did want to show you that there is an online grapher that's really nice and easy to use that can help you to be able to graph these relations. And so let's take a look at this one, x cubed plus y cubed equals negative 65. And you might be thinking, well, what does that even look like? So what you can do is go ahead to whatever search engine you have and just type in Desmos is the program. For those of you guys that have never heard of it, Desmos is an online, basically a computer algebra system that does a lot of things for you. And just type in Desmos implicit relations in 2D. And the first one that comes up is this Desmos calculator. Right? So just click on this one. And you can just click on any of these. And what you can do is you can go ahead and graph what they look like, what these different functions or different relations look like. Clearly, they're not functions because they don't pass the vertical line test, but these are all just examples. This is the iHeart Math example, I suppose. But we're interested in x cubed plus y cubed equals negative 65. So let's see what that looks like. X cubed plus y cubed equals negative 65. And we have to click right here in the circle to graph it. And this is what it looks like. Now what I'm going to do is I'm just going to zoom out, right? And it just has this this little bump in it. So it's not really all that exciting of a graph, okay? But it is what it is, all right? And remember we were looking at the point -4, -1, right? So we go back here to maybe this point right here, right? We're looking at the slope right here, and it was -16. And that makes sense because it's almost a vertical tangent or a vertical slope at that point, which makes a lot of sense that it should be that rapidly declining. Right? So hopefully this helps you to be able to take a look at the different types of relations. And I would suggest going through and just playing around with some of them. They're actually, a lot of them are really cool. For instance, there was another one that was in here, x cubed plus y cubed is 1. It does that sort of shape. And you can kind of get an idea of what happens as you start changing the coefficient. So instead of 2, let's make it 55. And it starts getting like a bigger bump there. So we can make it 100, and 1,000, etc. So pretty cool that we can just go ahead and if I did 0.1, or 0.01, or 0.001, it's pretty neat how these implicit functions just basically have their own magnitude to where we're almost multiplying it by a scalar for whatever that constant is. Anyhow, I want to go back and take a look at two more examples of being able to work with these implicit derivatives, so that way you have a little bit more difficult examples under your belt. So let's say we have this one. We have 2 sine xy equals 9x plus 7y. And so let's find the derivative of this thing. Now we have to be careful because this one's a really sneaky one because we have a chain rule, because we have an interior function. And also, not only do we have a chain rule, but we have a product rule that's going on in here, right? So this might be the toughest implicit derivative that we have, because we have chain, we have product, but then we also have implicit. All right, so this is a pretty tough problem. So let's get to it. Derivative of the outer function, which is f, is going to be cos. So that's easy. So 2 cos. We're going to leave the inside the same. And what I'm going to do is I'm going to just write this as xy prime for right now, because I don't want to take the derivative yet of this thing. On the right-hand side, the derivative of 9x is 9. The derivative of 7y is 7. But because there was a y originally in there, we're going to multiply that by dy dx. Okay, so just be careful with that. Now we're going to go ahead and take the derivative of what's in here, and that's going to be a product rule. So I'm going to define little f to be x. I'm going to define little g to be y. The derivative of x is 1. The derivative of y is 1, but we're going to multiply that by dy dx. All right, so what does this turn into? Well, it starts to turn into a bit of a mess. So we still have our 2 cos of xy. But what happens with that interior, or that product of xy? Well, we're just going to use the product rule. And so from our product rule, f prime g, fg prime, that's going to be 1 times y plus x times 1 times dy dx. And on the right-hand side, we still have 9 plus 7 dy dx. And the goal is for us to be able to solve for dy dx. And how do we do that? Well, not easily, because now in the problem, there are 2 dy dx terms. So think back to Algebra 1. What did your teacher say when you had 2 variables on either side? Well, you want to get all the variables to one side, and that's exactly what we're going to do. We're going to start by distributing. Even though we don't want to, we're going to. We're going to distribute that 2 cos xy to both of the terms. I'm going to move the y in front. So this is going to turn into 2y cos xy. I'm not sure how this x got in here, but this x shouldn't be there. Plus 2x dy dx cos xy. And then finally on the right-hand side, we still have 9, 7 dy dx. All right, so it is a mess. Now we're going to get all the terms with dy dx to one side. So let's just move the 9 to the left side. Let's move the 2x dy dx cos xy to the left, to the right-hand side. And so now this is going to become 2y cos xy minus 9 is going to be equal to 7 dy dx minus 2x dy dx cos xy. All right, so it looks pretty complicated, but again, we're just doing some really basic algebra of moving things around. Now, notice on the right-hand side, both of the terms have a common dy dx in them. So what does that mean? Well, that means we're going to factor it out. So let's factor this. And I'm just going to afford myself a little bit more room. And so by factoring, we're going to get 2y cos xy minus 9 is going to be equal to, we're going to factor out the dy dx, and we're going to be left with 7 minus 2x cos xy. And now we have to solve for dy dx. So we're going to divide both sides by this 7 minus 2x cos xy. So our final answer to this, 2y cos xy minus 9 divided by the 7 minus 2x cos xy is equal to dy dx. Okay, tough problem. All right. In fact, one of the more difficult problems that we've done in this course. Right. So what I would suggest is before moving on to the last problem, maybe go back through, make sure that you're able to do this one. All right. And I'm not sure why that does that all the time, but regardless, but make sure you're okay being able to do the process of the implicit differentiation. Okay, so maybe watch this video again, at least starting from the point where we try to take the implicit derivative of this. And then the last problem we're going to take a look at, we are going to find the equation of a tangent line at a specific point, and then we can use Desmos to be able to graph the original relation as well as the tangent line on the same graph to make sure that they make sense.